First speaker today is Anup Dixit. He's from IMSc mathematics group, and he does number theory, and he will also be in the today evening. So enjoy.
Thank you, Sushmita, for the introduction. Good morning, everybody. So how is it going in IMSc? How was yesterday? Okay, good. Yeah. So we will. So this our first talk is going to be on some very elementary number theory. Elementary doesn't necessarily mean easy, but it just means that we won't use complex analysis or things like that. And we will talk about some problems which goes back millennia, in fact, not just centuries, and hopefully it will sort of encourage you to learn more in these topics. Okay, so first of all, I would like to thank the organizers for the invitation to give a talk here at FACEIT. It's really nice to talk to students. And I would start with, so the title of my talk would be some problems in the world of Diophantus. Now, Diophantus Alexandria is a mathematician, a very famous and old mathematician. We don't really know when he was born and when he died, but it is estimated to be around 300 BC. So that's around 2,300 years ago. But he. Sure. So that's okay. Let me not test their history here, but I'll come back to that. Yeah. Do you guys know where Alexandria is? Oh, okay. Well, not bad. Yeah. Okay. All right. So we will. So this was like in the very, very early days when even the concept of numbers was a big deal. You should know that numbers as such, what I feel is numbers is as old as human thought itself. As soon as we started thinking, numbers came into place. And as soon as numbers came into place, somewhere we were aware of the whole idea of equations, where we know we want to figure out what numbers satisfy certain properties, certain equations. Okay, so Diophantus was one of the major players in the foundations of number theory, and he worked on some amazing problems, and many of that is in fact not solved today. So today we are going to focus on three main aspects of three main problems that Diophantine looked at. He looked at many other problems. Of course, he didn't really put it in a as cohesive manner as we look at it today, but he definitely had the right ideas. So one would be Diophantine equations, the second would be Diophantine approximations, and third would be Diophantine M tuples. That's something that he introduced. And in fact, I will also give a theorem on Diophantine M tuples, which we have proved with some of my summer students, exactly as old as you. So directly bringing that to the mathematics of today. All right, so let's see how our equations are relevant. We have tons of word problems, so I just picked something in random. So let's say we have some camels and some ostriches walking in a desert. Their head count is 30, and their leg count is 80. So do you know how many legs an ostrich has? How many legs a camel has? Exactly, yes. So this is quite a simple problem. So how do we solve this? Yeah, so let's say the number of camels is X and the number of ostriches is Y, and their head count is X plus Y is 30. And similarly, the leg count, okay, we have assumed this is camels, so camels have 4 legs, ostriches have 2 legs, and that is 80. And we know how to solve a system of linear equation such as this. Can you tell me what's the final answer? 10, 20. Okay, so X is 10 and Y is 20. Absolutely, very good. So this is a very simple and a sort of like the first type of equations that we know. Basically, we knew two objects. One was camels, one was ostriches. We knew something about those objects, their head count and their leg count. Using that, we could figure out how many camels are there and how many ostriches are there. Okay, so let's go to, let me just say that, if you have linear equations of this type, then it is sort of easy to solve. In fact, you would have seen that things of the type, let me just say, a1x1 plus a2x2 an xn, let's say equals to b1. Let me put a11, a12. So if you have such a linear equations, such a system of linear equations, then under certain conditions on your coefficients a1 to an, which you are aware of, we can find solutions to this system, or we know that there are no solutions. So basically the coefficients capture everything about these equations. And a typical way to write these coefficients is in a form of a matrix. Let's call this matrix A. Now, if it is a nice enough matrix, and if there are n equations and n variables, and if it is a nice enough matrix, that is, it is invertible, then there is exactly one solution. And if it is not such a nice matrix, you would see in your linear algebra that sometimes there are solutions, sometimes there are many solutions, and sometimes there are no solutions. So that's the study of linear equations. Now let's make it more interesting and say that, okay, suppose we have just one equation and more than one variable. Then what happens? And such equations are called linear Diophantine equations. So here, so this is an example. So we suppose you have a, b, and d as integers. You are considering this equation ax plus by is equals to d, and you want integer solutions for x and y. Remember, we are not looking for solutions elsewhere. We want integer solutions. Such equations are called Diophantine equations. Let's look at some examples. Here are some examples. 12x plus 13y is 1, 13x minus 23y is something, 6x plus 9y is 53. Okay, so the first question is, does there always exist a solution to such an equation? What do you think? Yes? Need not be, okay. Why? Can you give me one example amongst the equations that I have written which does not have a solution? Yes? The third one, exactly. So 6x plus 9y equals to 53 does not have a solution. Why does it not have a solution? Exactly. So the point is we are looking for integer solutions. We don't want solutions in other in other fields, in other setup. So here, if you look at the left hand side, that is 6x plus 9y divisible by 3. Right side is 53, not divisible by 3. So no matter what x and y I choose, this equation will never be satisfied. And the next question is, suppose there is a solution, can we find the solution? And if we can find a solution, can we find all the solutions? So that is called a linear linear Diophantine equation. And let's first see how to find solutions of linear Diophantine equation. Okay, so here is the theorem. Only when we are not in this type of a setting where the coefficients are all divisible by a number greater than 1, and on the right hand side we have a number not divisible by that. If we are not in this particular trivial obstruction, then in fact there will always be a solution. So the theorem is that if you look at any linear Diophantine equation ax plus by equals to d, this will always have an integer solution if your d is divisible by the GCD of a and b. Okay. Now let's look at some example. So let's take an example. Let's say 54x plus 16y equals to 2. the GCD of 54 and 16 is 2. So therefore, this equation by the theorem should have a solution. And now our job will be to figure out how to find the solution. And there is a very classic algorithm which is called Aryabhata's algorithm, or some people called it inverse Euclid's algorithm. The people who are not aware of India's mathematical history, but it was actually first, the inverse Euclid's algorithm was first observed by Aryabhata, not Euclid. Euclid just figured out how to compute the GCD. So let's recall Euclid's algorithm first. So we basically write 54, divide it with 16, and whatever remainder we have, which is 6, we write it in this way. 54 is 3 times 16 plus 6. And then we continue the same thing with 16 and 6. So here's what happens. So 16 is 2 times 6 plus 4. And same thing continuing again. 6 is 4 plus 2. 1 times 4 plus 2. So basically this will tell you, and this is where we stop because 4 is divisible by 2. And this is telling us that 2 is in fact the GCD of these two numbers, 54 and 16. That's what Euclid's algorithm gives us. Everybody has seen Euclid's algorithm before? Okay, excellent. Now Aryabhata's algorithm is, we will start with 2. Using this set of equations, we will try to write 2 as a linear combination of 54 and 16. That is what we are trying to do here. So here's what we'll do. We'll start with the last equation. 2 is 6 minus 4. Then we already know that 4 can be written as a linear combination of 16 and 6. And we'll just replace 4 with that. That is 16 minus 2 times 6. And then we know that the 6 can be written as a linear combination of 54 and 16. And we will just do that. We will just replace my 6 as a linear combination of 54 and 16. And finally we end up with something like this. If we clean everything up, it becomes 3 times 54 minus 10 times 16. And that is equals to 2. Okay, so that's the Aryabhata's algorithm, which is just inverting the Euclid's algorithm to write the GCD as a linear combination of both the numbers. All right. So now that is one solution, but you can ask, what are the other solutions? Are there other solutions to this equation? Are there other solutions? So one solution we got was x is equals to 3 and y is equals to minus 10. Are there other solutions? Louder, I cannot hear you.
The multipliers will
You multiply it with what?
like any number with same number, like 2 times 3 and 2 times minus 10.
Okay, very good. Let's try to work it out. If you look at 2 times 3, that is 6. 6 times 54 is 324. 2 times minus 10 is minus 20. Minus 20 times 16 is 300 minus 320. The difference is no longer 2, it's in fact 4. Right, if you multiply it with some number and multiply this with some number, then this will also get multiplied with that number. That's the issue. Yeah. Anyone else? How do we get another solution? Or are there other solutions? Okay, so let's try to do the following. I will add 16 to this. I will add, let's say, 54 to this, or subtract 54 to this. And let's try to see what happens. So this becomes 3 plus 16 times 54 plus minus 10 minus 54 times 16. So that is basically your 3 times 54 minus 10 times 16, that I'm getting from here. And then I have plus 16 times 54 minus 54 times 16. This will just disappear because they are the same numbers. subtracted from each one another, and what is left with exactly this. So using the fact that 3 and minus 10 are a solution, I can get another solution by just adding, by just adding 16 to 3 and subtracting 54 to 10, minus 10. Okay, does that make sense? Yeah, you need to be a little more reactive so that I know that it makes sense. It might be too easy, it might be too difficult, but just at least nod if everything is okay. Okay, so basically the point is, once you have a solution of this type, then I can produce another solution, let's call that x naught, as 3 plus some 16 times some number k, and another solution y naught as minus 10 minus 54 times the same k. If I do that, then plugging x naught in place of x is going to give me exactly 54 times 3 plus 54 times 16k, and on the other hand, when I substitute y naught in place of y, I get 16 times minus 10, and the other one is minus 54 times 16k. Minus 16 times 54k minus 16 times 54k cancel out, and this is another solution. And what turns out is that these are the only solutions. So that's the theorem, that if you have one, you need to account for the fact that the GCD is 2, so you can in fact take 8k here, sorry about that. So in fact all the solutions are exactly of this form. You have 3 plus 8k and minus 10 minus 27k. 27 is 54 over 2. Yes? Sorry, what? Oh, the screen is gone. It will come back. Okay. Okay. Yeah. Okay. Until then, I can just write it over here. So all I'm telling you is that you already had 54x plus 16y equals to 2, and we had a solution x is equals to 3 and y is equals to minus 10. Then I'm telling you all the solutions are exactly of the form 3 plus 8k and minus 10 minus 27k. For any integer k, if I plug in any value of k, that will give me a solution here. And that's the solution for linear Diophantine equations. Have you seen this before? This is familiar to you? So this is what is Aryabhatta's algorithm, writing down the GCD as a linear combination and giving all possible linear combinations, which ends up being the GCD. Okay, so first thing I will do is I'll try to give you another way of doing the same thing. Okay, finding another way of computing x and y for a linear Diophantine equation, and that will be through what is called continued fractions. So let me first tell you what a continued fraction is. And continued fraction is a fraction of this particular kind, which looks of like this form. These are called standard continued fractions. A number which is written in this form, when you write a rational number in this form, this is called a continued fraction representation. You can actually write all real numbers in this form. We will talk about that. But this type of a representation is called continued fraction. So let's just see an example, and we have already seen one example. So let's we already want to find what is the solution for this 54x plus 16y. We already have the solution here, and I'm going to show you how to do it using continued fractions. And this is what we do. So first realize that 54x plus 16y is 2 if and only if I take out all the common factors. 27x plus 8y is 1. Okay, so now I'll write down the continued fraction for 27 over 8. So how does that work? So if I have 27 over 8, and I know that 8 times 3 is 24, I'm left with 3 over 8. Then I write this as 3 plus 1 over 8 over 3. And then I have 3 plus 1 over 3 times 2 is 6. So 2 plus 2 over 3. And I keep doing that. So then this becomes 1 over 3 over 2, which is 1 plus 1 over 2. That's what I have there. Okay. So this is the continued fraction of 27 over 8. And in order to find the solution, what we do is we just erase the last number that we get here. Like over here, I'll just erase this 1 over 2. And whatever is remaining, I will evaluate it. So if I erase 1 over 2, what is remaining is just this part. 3 plus 1 over 2 plus 1 over 1. Okay, the indentation is a little weird, but okay. And if I calculate it, if I calculate what fraction it gives me, 2 plus, let me just calculate it here anyways. So this becomes, your 2 plus 1 is 3. So 3 plus 1 over 3 is just 10 over 3. And 10 and 3, if you remember, they were exactly our solutions. Minus 10 and 3 were exactly our solutions. And that is what we get immediately. That if it is 10 over 3, then in fact 27 times 3 and 8 times 10 should differ by exactly 1. So that will be a solution for 27x plus 8y equals to 1. Okay? Is the strategy clear to everyone? Write the continued fraction down, then forget the last entry and evaluate the whole thing. Whatever you get, that is one solution. That is exactly one solution. Now, if you actually sit down and think about it, this is nothing but your Aryabhata's algorithm, but this is a more finer way to do it and impress students. Yes.
How are we supposed to know that it will be minus 10?
Okay, that's a good question. And the thing is, you will not know. Sometimes it will be minus 10, sometimes it will be plus 10. And here is the general rule. So suppose you have ax plus by equals to 1 and you want to find its solution. Write down a over b. Let's say you get something. All right, suppose this is your a over b. I forget this. I calculate the rest. And let's say you get p over q as the rest. Then what you can conclude that your aq minus bp is either 1 or minus 1. It will be one of the units. It's either 1 or minus 1. So it is very much possible that if you just evaluate the continued fraction, sometimes you may get minus 3 and 10 would give you 1. Well, not hit and trial as such. It will either be 1 or minus 1. So it's not exactly it's a concrete thing. So it actually depends on when you terminate. If you are taking 3 steps, if you're taking like 3 steps, then you have to take a negative, or if you take 4 steps, you have to take a positive. It will depend on where you terminate. So there is a pure algorithm. There is no hit and trial here. Yeah. Okay.
27x plus 8y is equal to 1.
Yeah.
And we just put x at one side and take the rest over to the other side. We get 1 minus 8y by 27 is x.
Yeah, that's right.
So if we find a solution for 1 minus 8y mod 27 is congruent to 0.
That is exactly what it is. Yeah. So Euclid's algorithm is what? It is basically finding the inverse of a number modulo another number. It is exactly the same thing. You're right. Yeah. But again, how do you find the inverse? Basically, you have to do this business at some point.
So if you show that the solution exists, right?
Yes, solution existence is not a problem. As soon as your things are relatively prime, its solution will exist. Correct. Okay, any other question? All right, so that's this is more like a magic using continued fraction to get solutions. And in fact, one thing you should note here. Okay, I put it as a note, but that's because what is going to come next. Any rational number, anything of the form a over b, can be written as a continued fraction, and the continued fraction will have just a finitely many terms, just like whatever you have seen before. So just to answer your question on what happens in general when I want to, we just saw an example. I'm just going to write the more general algorithm. We are not proving it. I'm just giving you the algorithm, but you can try to prove it. It's not that difficult. So we want ax plus by to be 1, a and b are given to be relatively prime. So the solution exists. Now you just write down your a over b as a continued fraction. Then you forget the very last term. And whatever is remaining, call that p over q. Then aq minus bp should be either 1 or minus 1. And that 1 or minus 1 will depend on whether your n is odd or even. Basically. Okay. Any questions so far? All right. So now we are familiar with this finite continued fraction. Let's just, now that we are in the realm of continued fraction, let's say a little bit more about continued fractions. There are also infinite continued fractions. And here is an example. The simplest type of a continued fraction you can think of is just put all the entries as 1. Do you know what x is? Can you figure out what x is from here? Yes? Exactly. So we will use the fact that your x is 1 plus 1 over x. So first off, in order to use recursion, you should be able to say that representation, that continued fraction representation should converge. But let's not worry about convergence. Take it from me, it will converge. So you have your, this is your recurrence that you get, x equals to 1 plus x. This is just a quadratic equation, and you can figure out what the solution is. Solution is 1 plus root 5 over 2. Okay, so the other solution we will not take because that's a negative number, and here all the entries were positive, and this is positive. So this was an irrational number, and we had a continued fraction representation of an irrational number. Okay. So that was an infinite continued fraction representation. All right, so any questions so far? Okay, so how do we write down an irrational number? So this was like you give me a continued fraction which was nice enough, and I could figure out what number it represented. But suppose I give you a number and I ask you what its continued fraction representation is. How do you do that? Again, it is fairly easy, exactly the way we were doing it for rational numbers. So let's say you are given square root of 2, because that's one of the easiest numbers to write down. So look at, we already know that square root of 2 is 1 point something. So I can write this as 1 plus square root of 2 minus 1. Now this square root of 2 minus 1 is a number which is less than 1. So this is 1 plus 1 over instead of writing 1 over, I'll just multiply the numerator and the denominator with square root of 2 plus 1. Then this becomes 2 minus 1, that's just 1, and you get square root of 2 plus 1. Okay, so that is my first step. Now you look at how big is your square root of 2 plus 1. Square root of 2 plus 1 is going to be 2 point something, because square root of 2 is 1.4 something. So this is 2 point something. So I will write it as 1 over 2 plus this square root of 2 plus 1 minus 2, which is again square root of 2 minus 1. And then I can just repeat what I did. So I have 1 over 2 plus, again square root of 2 minus 1, I can write it as 1 over square root of 2 plus 1. And if I keep repeating, is that okay? Okay, so basically the point is we take a number and look at the closest integer which is less than that number. Put that integer, that has to be a positive integer, and then whatever is remaining is a number between 0 and 1. So we take its reciprocal, and once you take the reciprocal, the thing in the denominator is again greater than 1. So we take the closest number which is less than that. Closest integer, smallest positive integer is less than that. Repeat the process, you will get a continued fraction. This process you can do for any real number. Okay, so if you start with a negative number, then only the first thing is going to be something negative, and the rest of the things will again be positive. Okay, so this is the standard continued fraction representation, and I have whatever I said, I have just written it down here. So finally we end up with a continued fraction of this type. Is that okay with everyone? Any questions? Okay, so where are these things going? Keep in mind that we were talking about Diophantine equation. Somehow we need to bring that back, and it will come back. So don't worry, we are not going astray. All right. So this is how you write a continued fraction of a given number. And in fact, for any real number, as I said, maybe I'll just repeat myself once again. Suppose I start with any real number. And let's say your alpha naught is the largest number, which is the largest integer, which is less than alpha. So that means your alpha minus alpha naught is actually less than 1. Strictly less than 1 and strictly greater than 0. Then I'll write my alpha as alpha naught plus alpha minus alpha naught. So this is a number which is between 0 and 1, and I'll just take its reciprocal. Now this is a number between 0 and 1, so its inverse is a number which is greater than 1. So I will repeat the process. I will say alpha 1 is the greatest positive integer, which is less than alpha minus alpha naught inverse. So the difference between this alpha minus alpha naught inverse and alpha 1 is going to be a number which is between 0 and 1 again. So that's what I'll do. So then that is going to be my next entry, alpha 1 plus the difference, alpha minus alpha naught inverse minus the alpha 1. And this whole thing is a number which is between 0 and 1, strictly less than 1. So again I can do the same thing. I can take its inverse. So it will, and the process will continue. The whole thing inverse, alpha minus alpha naught inverse minus alpha 1 inverse. And this entire thing is a number which is strictly greater than 1. So again I take out the largest integer part, and then whatever is remaining, take its inverse and continue. That's how I write the continued fraction representation for any real number. Okay? Does that make sense, or is it confusing? It's okay? Give me some nod, or just say no, we don't want to listen to you anymore. Give me. Okay. All right. So that's what we have. So basically, what we have just shown is that every real number can be written as a simple continued fraction. The reason I keep calling it simple is because there are other types of continued fraction, but we are only going to talk about this type of continued fraction. So, and these type of continued fractions are called simple. Okay. And your continued fraction should be finite if and only if it's a rational number. That's what we saw. For any rational number, it terminates. All right, so we saw some special type of continued fractions, that is continued fractions for root 2. For root 2 is the only thing we have seen, and it turns out that if my continued fraction is periodic, like suppose I have, let's say 2 plus 1 over 1 plus 1 over 3 plus 1 over 1 plus 1 over 3 plus 1 over 1 plus 1 over 3, this type of thing. Suppose I have some kind of a periodicity, like 1 3 1 3 is appearing, is repeating itself. So this type of things is called a periodic sequence. So the sequence that I write down, 2 1 3 1 3 1 3 1 3. So this is a periodic sequence. So it turns out that if your continued fraction, the representation of the real number is periodic, Then, in fact, it is eventually periodic. The first few things we don't care. Eventually, it becomes a periodic representation. Then it has to be a quadratic irrational number. We have already seen that your square root of 2 was something which had a continued fraction where it was quite nice. So it was something of this form. Here it's just 2, 2, 2, 2, 2. So it is periodic with period 1. So 2 is repeating itself. Similarly, this was a much simpler case, but if you take root 3 or something, we will see one example. Then we will have a continued fraction which is again periodic. So periodicity implies that it is a quadratic irrational. What is a quadratic irrational? Quadratic irrationals are numbers of the form like root 2, root 3, or you know, like something like a plus b root d, some number of this form. But not combinations of both. You can't say root 2 plus root 3. That's not quadratic anymore. Yeah, like 1 plus root 5 is a quadratic number and things like that. You can take a rational number, that's fine. 1 plus root 5 over 2, that's okay. Okay, so let's see one example. One example is that of root 3. Root 3, if I write down its continued fraction representation, again, root 3 is a number between 1 and 2, so I take out 1, whatever is remaining, I take its 1 over its inverse, and I keep doing that. Then I get this particular representation where my 1, 2 keeps repeating. So this is a periodic sequence. So this is a theorem of Lagrange. And so what we know is rational numbers have a finite continued fraction representation. As it becomes periodic, it is a quadratic number. It's quadratic irrational. Okay, so the reason we have started talking about all this is because representations of this quadratic irrational has something to do with solving Diophantine equations, some special type of Diophantine equations. And that's what we are going for next, because the current theme is Diophantine equations. Okay, any questions? Any questions? Yes, there is a question. That is correct, yes. It is by quadratic irrational, I mean it's the root of a quadratic polynomial, yes. X square plus b plus bx plus c. That's right. Yes.
Find congruent number using Diophantine.
Yeah, just remind me what is congruent number?
An example in which we can find whether a number is congruent or not.
Yeah, just remind me the definition of congruent number. I don't remember it.
The area of a right angle triangle.
Right angle triangle with rational sides. Yeah. Oh, you're saying can we do something about that using continued fractions? Is it, or using Diophantine equations? I don't know, but yeah, we can maybe talk about it afterwards. Okay. Yes. Any other questions? Yeah. All right, so let's move on. Okay, because it is periodic, we can talk about the smallest length or smallest, the length of the period, which is in this case it is 1, 2 is repeating itself, so the length is 2. Similarly, if you have some other number, it may have a length 5 or 6. Now the natural question is, what is the length of the square root of d? This was a question which was in fact looked at long time ago, 1600s or something. And the answer to that is we still do not know. We have no idea even how to find bounds for this lengths of quadratic continued fraction representations of quadratic irrational numbers, and it turns out to be a very difficult question. It has something to do with what we call regulators of a quadratic field, which are very difficult objects to get your hands on. Anyway, so that is just some open question over there. If you can figure out the length, that will be great. All right. One other definition that we need is what are called convergence of continued fractions. So convergence just means that we terminate it at some point, calculate the rational number and see what it is. So like for example, the first convergent is A1. The second convergent is just take A1 plus 1 over A2 and then take 3 terms. So you will keep getting some rational numbers, and these rational numbers are going to converge. So this P1 over Q1, P2 over Q2 is just taking 2 terms, Pn over Qn is taking the first n terms. So these rational numbers will converge to your alpha, to the entire number, entire representation that we have there. Okay, so that is something that are called convergents, and so that is some kind of a rational approximation for the number alpha, right? Continued fractions, and this is one of the rational approximation. And soon we will see that this is the best possible rational approximation. Any number, any real number has a rational approximation. How did we construct real numbers? We started with rational numbers, patched everything up, made it complete. So everything which was like a limit of a sequence of rational numbers, we call them a real number. Now there may be several sequences of rational numbers which converges to one particular real number. Now we say an approximation is nice if your let's say we say, suppose limit of, in this case, let's say n going to infinity, Pn over Qn is alpha. So this alpha is a real number. This is one of the rational approximations. The rational approximation is nice if alpha minus Pn over Qn is very, very small. Let's say if I can say this is less than 1 over Qn square, for example, then this is a good rational approximation. Trivially, I can say it is less than 1 over Qn, but that is not a good rational approximation. But if I can say it is less than a power of Qn, let's say Qn square, that is a good approximation. And it turns out that this is the best that you can do. If I replace this with 2 plus epsilon, then you can show that there are in fact, if you take any algebraic irrational number, there are only finitely many rational numbers which satisfy this inequality. So a good rational approximation is an approximation where you get a very, very small number on the right hand side when we are approximating it through these type of rational numbers. Okay, so they are going to that real number extremely fast. Now it turns out that your continued fraction representation is the best possible rational approximation you have. Compare that to your decimal representation. Okay, so decimal representation, actually I'll just write it here. For example, if I write a number, let's say 2.14359 so decimal approximation is what? First approximation is 2.14, then 2.1, then 2.14, 2.143. These are all rational numbers and they converge to my given number alpha. But at any stage, if I look at 2.1 minus alpha, then the remaining part is of the order 0.1 itself. Is of the order 1 over 10. So that is basically the decimal value that you have here. This is 2 plus 1 over 10. And then this minus alpha would all you get is this is less than 1 over 10. If I take 2 more things, 2.14 minus alpha, that is less than 1 over 100. So here this was what? This was 2 plus 1 over 10 plus 4 over 100. So my denominator was of the order 100 and I get that is less than exactly 1 over 100. So these the decimal expansions, you can say they are bad rational approximations of real numbers. However, continued fraction expansion are excellent rational approximation. In fact, they're the best you can do. That is something which you should keep in mind. That's why it makes it so good. That's why it is so important. So this is a subtle point. In case you missed something, don't worry about it. I will repeat itself later. Okay. So convergence of continued fraction, this is just an example. So if you have root 3, then 1, 2 over 1, 5 over 3, 5 over 3 is like taking 3 terms, then 7 over 4 is taking 4 terms, so on and so forth. These are the convergents. And if you actually notice, this will converge to root 3 very, very fast as compared to the decimal expansion of root 3. Okay, so these are some properties of convergent that we have. In case you're taking notes, I'll just wait for 1 second and you can ask me any question if you have. All right. So here are some properties of convergence. So the Pn divided by Qn is you take the first n terms. So the difference between Pn over Qn and Pn minus 1 over Qn minus 1, that's the difference that, that is the rate at which it converges. That is actually going to be of the order 1 over Qn times Qn minus 1, plus minus 1 up to. So using this, you can actually show that the approximation is as fast as 1 over Qn square. That's the Diophantine that's the rate at which it converges. And in fact, if I stop it at a given point and see what sort of approximation I get, it is monotonically increasing and decreasing. That's how it is approximating the number. So if I take the first two terms, let's say it is slightly greater than my alpha. Take first three terms, it is slightly less, and things like that. Okay, so this is so we get, if you take the odd or just the odd convergents, they are monotonically increasing. The even convergents are monotonically decreasing. Okay, is that okay? Any questions? Did it go too fast? Should I go a little slower? Yes, it's fine. Okay, good. Yeah, just give me some response so that I can go ahead. So yeah, all the story about continued fraction brings us back to another type of Diophantine equation. Now we are no longer in the linear Diophantine equation case. We are in the quadratic Diophantine equation case, and the simplest quadratic Diophantine equation is Pell's equation, Brahmagupta-Pell's equation. Again, Brahmagupta was the person who gave the algorithm how to solve these equation, which in the West is known as Pell's equation. But it's good to know our history a little bit. Actually, I'll just write it over here. It's fine. Okay, so these are equations of this type: x square minus dy square equals to 1. Again, d is some number, some positive number. And we would like to find solutions to these equations, integer solutions. So the first question is, does there always exist a solution? What do you think? Yeah, so what do the majority of you think? Does there always exist a solution? Raise your hand. So there does not exist a solution? you will not vote? Okay, there does not exist a solution. Okay, let's see what happens. So it seems that the solutions to these numbers are captured by, okay, I kind of wrote it in this way. So it turns out that there will always be a solution to this equation for any d, and the solutions are precisely captured by your continued fractions. Yeah, so sorry to disappoint people who did not want solutions. All right, so let's see from whatever we have learned about continued fractions how to find solutions of this Diophantine equation. Oh yeah, before I go there, the theme that we just talked about of approximating a real number through continued fractions or even any rational numbers, those type of things, the study of these type of things is called Diophantine approximation. That is also a theme which I am clubbing in the Diophantine equation setup. But those two things were thought of first time by Diophantus. Okay. So here, let's see how it is captured by square root of t. It's best to give an example. So we had already figured out the continued fraction for root 3. So I will use that. So let's look at the equation x square minus 3y square equals to 1. And I told you that the solution is captured by the continued fraction of square root of d. Here it is square root of 3. Square root of 3 is given by this continued fraction, 1 plus 1 over 1 plus 1 over 2, 1, 2, 1, 2 keeps on repeating itself. Okay, so now these are the convergents of the continued fraction. So we would like to know the solutions. Okay, I'm telling you, let me tell you that the solutions are hidden in these convergents. Now can you make a guess? 2 and 1, absolutely. So 2 and 1 is a solution because 2 square is 4 and if I take y equals to 1, 4 minus 3 is 1. Can you give me another solution? 7 over 4, absolutely. Okay, that's 49 minus let's say 48 because that's how it should work. Okay, so in fact it will turn out that all these even convergents would be the solutions to this Brahmagupta-Pell's equation or Diophantine equation. All right, so I'm again not giving you a proof of why these are the solutions that you can figure out, but this is an algorithm to find all the solutions, and these are precisely all the solutions that you get. So all the solutions are going to be the even convergents. In this case, it will be the even convergents. That's not the case all the time. Okay, so this is a very clean way of finding solutions of Pell's equation. But if I did not give you this algorithm to find solutions of this type of equation, it's actually not very easy. You can try to come up with methods to find its solution. It is not at all easy. And I'll give you one anecdote proving it. This is a story of Srinivasa Ramanujan, because he's the most famous mathematician that India has produced in early 20th century, and his story is highly jazzed up. So why not talk about him a little bit? Ramanujan, as a genius as he was, there is a very nice anecdote during his time in Cambridge, and this is a puzzle that came in one of the newspapers in Cambridge. Let's first read the puzzle, then you can think about it a little bit while I'll give you the story. So the puzzle says the following. So on a street in the town of Louvain in Belgium, one of the house numbers had this peculiar property that the total number of numbers lower than that was equal to the total number of numbers above it. So furthermore, the house number was between 50 and 500. So on that street, the number of houses before that, if you add the numbers, and the number of houses after that, so the sum of this is the same as the sum of that. So find the number of this house and the total number of houses on that street. So my houses are numbered from 1 to something. I want a number in between such that the sum of the previous ones is exactly same as the sum of the houses which appear on the right hand side. Okay, so this appeared as a newspaper puzzle, and Mahalanobis was in Cambridge during that time. Do you guys know who P.C. Mahalanobis is? Yes or no? Have you heard of him? No? Never heard of him? Yes, yeah. Absolutely. He's the founder. He's the one who started ISI. He's one of the most reputed statistician and a mathematician of India. And he's the one who started ISI during our 1950s. It's a very, very big name. You should know about him. All right, so he was also there, and I think if the story goes right, Ramanujan was making upma, and he was there, and he asked him this question, and I'm working on this. Can you tell me can you give me the answer? Ramanujan, while making his food, immediately said, I can not only give you the solution to the question, I can give you all the solutions. And it is precisely continued fractions. And of course, if you don't know it, it is probably hard to solve these type of equation. But if once you know it, it's actually pretty easy. And if I have already given you the algorithm, it's easy to calculate. So let's try to figure out how to solve this question. So let n be the house number of that peculiar house, and m be the total number of houses. Then what is given to us is that the sum total of all the numbers before n, that is 1 to n minus 1, is same as n plus 1 to m. And what is the sum 1 to n minus 1, 1 plus 2 up to n minus 1? N into n minus 1 over 2. And by similarly, we get this is m into m plus 1 over 2 minus n into n plus 1 over 2. You're very good at simplifying equations, so you can simplify it, and this is what you get. 2m plus 1 square minus 2 times 2n square is equals to 1. Does this look like a familiar equation now? This is just, yeah, exactly. This looks like Brahmagupta-Pell's equation, x square minus 2y square equals to 1. So that's what it is. So these are just the solutions to the Brahmagupta-Pell's equation. So just for completeness, let's try to figure out what the solutions are. Again, square root of 2 is something we already knew how to find the continued fraction for, and this is what it is. Okay? So we will write down its convergents: 1, 3 over 2, 7 over 5, 17 over 12, so on and so forth. And remember that we were after solutions of x square minus 2y square equals to 1. So what are the solutions? Can you see some solutions in the list? 3 by 2, correct? Okay, now that you have seen a pattern, so okay, these are all the even convergents are going to give you solutions. But remember, in the puzzle, it was also one of the conditions was that the value of that house number is going to be between 50 and 500. So if you calculate it, only one of these satisfies that 50 over 500, that is this particular case, and you will get n is equals to 204, and the total number of houses is 288. Okay. Okay, any questions here? All right. So now let's look at what is the general solution of Pell's equation. It's not always the case that you just look at the even convergence. That is not how it works. It worked out in these two examples. So the general case is as follows. For those of you who are taking notes, I will just give you one more minute. Yes. Okay, it's good with everyone? All right, so this is the general principle. So we want to look for solutions of x square minus dy square equals to 1. And let's say this is the continued fraction I have for square root of d. Okay. Now it is square root of d, so it is a quadratic irrational number. Oh, okay, you have to assume that d is not a square, otherwise there is a problem. But yeah, so I think you also need to assume d is square free, if I'm not mistaken. Okay. Anyways, whatever it is, actually, you can always put that in the y. Okay. Yeah. Anyway, so d is not a square. So you can write down square root of d in this particular way. Actually, you just in this particular equation, you need to assume that your d is square free. Oh, I forgot to put that. Put that condition here. Suppose d is not square free. D is square free means that there is no square which divides d. If d is not square free, just write d as m square times n, where n is square free. And then whatever solution you find, you can always put you can substitute m times y as y prime and then work with that. So x square minus dy square would just be equals to x square minus n times my square. So it is exactly the same whether, so you can always reduce it to a question where we are looking at square free d's. So that's a condition that is missing, sorry about that. But let's just work with simpler cases. Assume d is square free. I want to find solutions of x square minus dy square equals to 1. So let I write down the continued fraction of square root of d. Let's say it looks in the following way. Of course, this is a quadratic irrational, so it is going to be recursive. I mean, it's going to be, it's going to be periodic. So I can catch hold of the minimal period. And let's say the minimum period is m. So that means, let's say, like eventually, let's say a1 to a2 ... there will be a length m which keeps repeating itself. Okay? So that's what is repeating itself. Let's say that length is equals to m. Then you have to look at the mth convergence, and that will give you the solution. So in case when m is even, you have to look at the mth convergence, like Pm minus 1 over Qm minus 1, P2m minus 1 over Q2m minus 1, then 3m minus 1 over 3m minus 1, and so on. And if m is odd, you have to look at the double of that, like 2m minus 1 over, so this will be the 2mth and 4mth convergence, 6mth convergence. Okay, so just write down all the convergence, pick the solutions depending on, at regular intervals of either m or 2m, depending on whether m is odd or m is even. Just remember that in your case when we had square root of 2, here 2 is an even number. So we were just looking at the second convergent, the third convergent, and yeah, so okay, anyway, so maybe the ordering is even or just that maybe is, one needs to swap that. So for root 2, you have to look at the second convergent, fourth convergent, and so on. But for root 3, where the minimal period is equals to 2, you just have to look at the second convergent, all the multiples of m, second convergent, fourth convergent, sixth convergent, and so on. I think this must be changed. This is odd and this is even. Yeah, anyway, just double check this out. So the point is that if you just write down all the convergents, they will give you the solutions of x square minus dy square equals to 1. But it's not like all convergents will be the solution. It will either be the mth convergence or 2mth convergence that you have to look at. All right, any questions so far? Okay, so in the discussion of this context, I should also mention that for the continued fraction representation, we already know that if it is periodic, it's a quadratic irrational, and if it determinates, it's a rational. You can ask what happens for other numbers. We know that all real numbers has nice continued fraction expansion. Is there some nice enough continued fraction expansion for other numbers? It turns out that yes, sometimes some continued fraction representation are really, really nice. And I think I'll give you one example just because everybody really likes it, and I also happen to really like this numbers continued fraction. So this is the number e, which is one of our favorite numbers in mathematics, and its continued fraction looks like the following. So we know that e is 2.7 something something, so it becomes 2 plus 1 over 2 plus I think 114 and then 116 and so on, something like that. Yeah. Just make sure that the number of ones are okay, but it goes in this particular format. There is 1, 2, then 114, then 116, 118, something. So that's the continued fraction expansion of e. And e is definitely not a natural number, not a rational number or a quadratic number. It is in fact not an algebraic number to begin with, but this has beautiful continued fraction expansion. Okay, so that's a second type of Diophantine equation, x square minus dy square equals to 1, a quadratic Diophantine equation, and we learned how to find solutions for that. So just one particular thing about Diophantine approximation, something we talked about in not much detail, but I thought I would mention it here. So Diophantine approximation is the study of rational approximations of real numbers. Okay. So when you take alpha, which is some irrational number, we know that it has some kind of a rational approximation. So there's some series of rational numbers which converges to alpha. Can you find the best possible approximations to alpha? So it was Dirichlet who in mid 1800s showed that if you take any irrational number, you can find many Pn over Qn, many rational numbers, which gives you this type of a rational approximation. Like alpha minus Pn over Qn is actually less than 1 over Qn square. This is much better than decimal expansion. Decimal expansion just gives you 1 over Qn. So with this, we have already seen the proof of this. Can somebody tell me what is the proof of this? Can you give me a proof of this statement? Start with a real number which is not a rational number. I want to find infinitely many rational numbers which are this good approximation of that real number. No, don't give me example. I want a proof, and we have already talked about a proof of this. Yes? So there's only one thing that we talked about, that is continued fractions. So let's just write down a continued fraction, look at its convergence. And I did tell you that these convergents actually approximate the continued fraction exactly this closely, this good approximation they are. If I take Pn over Qn as just convergence, then alpha minus Pn over Qn should be less than 1 over Qn square. And of course, this is an infinite continued fraction, so you have infinitely many rational numbers that you can just terminate at any point, get a rational number. It's a very good approximation of your alpha. Okay? So the proof of this is precisely continued fractions. The fact that there is a continued fraction representation is a proof. Okay, just think about that. I mean, of course we didn't prove it, but we kind of said that's a property of continued fractions. Okay, and then my point is that it seems this is the best rational approximation that you can get for all real numbers. So that is to support that, there is a theorem of Liouville which says that if you give me an alpha, then it cannot have this good rational approximation. Okay, suppose you give me alpha which is not a rational number, you cannot find too many rational numbers p over q such that alpha minus p over q is greater than some constant divided by q to the n. Okay, but here your n is actually the degree of, we have to be careful about what n is. If I take cube root of 2, I have to take my n as 3. So this is not as great. But then in more recent times, which is known as the celebrated Roth's theorem, he got the Fields Medal for this theorem, it says that we cannot have, I did mention Thué, Ziegel, Roth because everybody did contribute to this problem immensely. Now, we cannot have too many rational numbers which are excellent approximations of alpha. So if I start with some alpha which is an algebraic number like square root of 2, square root of 3 something, we don't work with things which are like e or pi. Take a nice enough algebraic number, it cannot have too many good rational approximations. If I ask you alpha minus p over q is greater than some constant over c to q to the 2 plus epsilon, just a little bit better than what your continued fraction gives you, you can tell me that that can happen only for finitely many rational numbers, cannot happen for infinitely many. So continued fractions is the best rational approximations for all real numbers. That's something you should keep in mind. Okay, so this is one thing I wanted to highlight. This is the theory of Diophantine approximations. And now in the remaining 15 minutes, I'm going to talk about something else which is called, there is something else remaining in between. Alright. So, okay, then there's another Diophantine equation. Let's talk about that for a short while and then I will go to the last part on Diophantine M tuples. So this is another quadratic Diophantine equation which is more popular, so I thought I will include that in the slides, which is Pythagoras, integers which satisfies Pythagoras theorem. So these numbers in positive integers which satisfy the equation a square plus b square equals to c square are called Pythagorean triplets. Do you know how to find all Pythagorean triplets? Like 3, 4, 5 is a Pythagorean triplet, 5, 12, 13 is a Pythagorean triplet. There is a way to find all Pythagorean triplets. So here's what we will do. We will first assume that your A and B are co-prime. If they are not, just either if C is not divisible by the co-prime, there is no solution. So you take out the common factor. Okay. So you can assume A and B are relatively prime. Then you write down A square plus B square as A plus IB times A minus IB. Now what you should notice here is that these two numbers have the same GCD as A and B. So I should tell you that the integers including I, Zi is actually a nice enough Euclidean domain. We can have the concept of GCD there. So these have the same GCD. So let's try to use that. So they have the same GCD, and that is 1. So the product is a square and they have the same, a product is a square and their GCD is 1. So what does that tell you? A plus IB times A minus IB is a perfect square, and both of them have GCD 1. That means?
One is 1 and the other is 6 squared.
Sorry?
One is 1 and the other is 6 squared.
One is 1, why 1? I mean, it could be some other square, no? The one is C1 square, the other is C2 square. Okay? Correct. So that means both of them are perfect squares. One is C1 square, the other one is C2 square. Their GCD is 1. So they cannot share any factors, so that's what happens. So let's just try to use that. So your A plus IB is the square of some M plus IN. A minus IB is some square of M minus IN because they are conjugates of each other, so it will be of exactly of this form. So then just expand it out and write the real part, equate the real parts, equate the imaginary parts. You get A is M square minus N square, B is 2mn, and then plugging that in you get C is M square plus N square. So this is precisely all the solutions to Pythagorean triplet. Any three positive integers such that your A and B are co-prime, which satisfies the Pythagoras theorem, A square plus B square equals to C square, is precisely give all numbers of the form M square minus M square, 2mn, M square plus N square. Okay, so this is the solution of Pythagorean triplet. This people knew from long time ago. So from here one can easily see that if I take A to the some even power, A to the 2k plus B to the 2k equals to C to the 2k should not have any non-trivial solution. By trivial solution I mean 1 0 1 to the something plus 0 to the something is 1 to the something. Apart from that there is no other solution. Have you seen this type of an equation before? Yes? Fermat's last theorem. So immediately from the study of Pythagorean triplets we say that Fermat's last theorem cannot hold for even n. X to the n plus y to the n plus z to the n even is already solved, because they cannot satisfy the solution. So in that context let me just write down what Fermat's last theorem is, which is now called Wiles theorem. And Richard Taylor is the student of Andrew Wiles who fixed some last bit. So we have x to the n plus y to the n plus z to the n. It will not have any integer solutions as long as n is greater than 2. But this was a very special case, and many things had to come together in the correct fashion for the solution of this Fermat's last theorem, and it was, as you know, it was a very big deal. But there are many equations that you can talk about, Diophantine equations, which we would expect have no solutions, but there is no way to solve them. Like for Fermat's last theorem to have a solution, many things had to work. We really had some nice objects, modular forms, nice objects, elliptic curves, and there was some amazing connection between them which was seen. So it is an extremely special case. More or less in most Diophantine equations you will not even hope for such a special thing to happen. And so what should one expect? One should expect the following. One should expect this conjecture which is called the ABC conjecture, and it is regarded as one of the most important and most difficult conjectures in the theory of Diophantine approximation. And this was conjectured first by Joseph Ostelle and David Masser. Ostelle visits IMSc often, he's a good friend of IMSc. So, and the conjecture is as follows. Suppose I have ABC as positive integers and it satisfies A plus B equals to C. Then we need something called a radical. I'll define what a radical is. It's actually pretty easy. So radical is just the product of distinct prime numbers of a given number. Let's say radical of 20 is equals to 20 is 2 square times 5 square, so I will just multiply 2 times 5, so that is 10. So radical of let's say 40 is also 40 is 2 cube times 5, so that is also 10. So I'll just multiply the primes, the distinct primes which appear in the factorization, and call that what is called the radical. Then they conjectured that if you have this type of an equality a plus b equals to c in positive integers, then this c must be less than some constant times the radical of a times b times c to the power some 1 plus epsilon. Okay. So that is the conjecture. Now this is a very, very strong conjecture. First observation is that if you assume this conjecture, Fermat's last theorem can be easily proved. And the way you prove that is because of the following. So you will get z to the n is z to the n must be less than the radical of x times y times z. Now radical of x times y times z is going to be very, very close to z. Let's say x and y are of the same size as z, then it is kind of like z cube. But as I keep increasing n, I should get that z to the n is less than z cube shouldn't happen. Something of that or z to the n cube plus epsilon should not happen. This is a very strong conjecture. I just thought I'll put it there. It's okay if it is if there is too much of notation. You can always talk about it later. Anyway, so that's one of the holy grails of Diophantine approximations. And there are tons of open questions that we don't have any idea how to do. So these are different Diophantine equations. We have no idea how to solve. In many cases we expect there are no solutions. Many cases we expect there are infinitely many solutions, but we have no idea how to proceed these equations. But of course, if you assume the ABC conjecture, you can say very concretely what happens in each cases. All right. Okay, in the last 10 minutes, before actually I go on, are there any questions? Maybe I should take questions before I go on to the next thing. Okay, so we'll come back and we'll talk about some more elementary things again. So here is a set that Diophant has constructed. I'll just try to summarize it very quickly in 5 minutes or so. There is this peculiar set that Diophant has constructed, and the set has the following property. If I look at 1 over 16 times 33 over 16 and I add 1 to it, then it becomes a square of a rational number. If I do the same thing with 1 over 16 and 17 over 4 and again add 1 to it, becomes a square. In fact, you take any two distinct elements in the set, add 1 to it, it becomes a perfect square. So this is a set that Diophant has constructed in 300 BC, and he wanted to know if there are integers with this property. Can we have a set of integers of this property? I mean, a large set. Don't take just a and b and say ab plus 1 is a perfect square. That you can always construct. Can you have a larger set with this kind of a property? And this is called the Diophantine m-tuple problem, where m stands for the number of elements in the set. And then the question is, if there are sets of this property, how large can the set be? So let me just give a quick quick history of this problem. So we call this set A1 to AM as a Diophantine m-tuple if two distinct numbers AI, AJ, add 1 to it, becomes a perfect square. And we will take all integers. Diophant did not construct an integer tuple, he constructed a rational tuple, which is actually a much harder problem. So the first Diophantine tuple was constructed by Fermat. He gave this number 138, 120. If you notice, 1 times 3 plus 1 is 4. 3 times 8 plus 1 is 25. 8 times 120 plus 1 is 721. All of them perfect squares. And then Euler came up and said that, okay, here is a more general a quadruple, like a tuple with 4 elements, which are all perfect squares. And this is like a generalization of Fermat's, because if you take A equals to 1 and B equals to 3, you'll get Fermat's tuple. So this is Euler's result. So he basically said that if you give me any nice triple, I can always extend it to a quadruple. That's basically what his theorem is. And more recently in the 1900s, so now we are back in our 20th century, it was shown, this is not an easy theorem to prove, that if you give me 138, there is a unique way to extend it to a Diophantine quadruple, and that is exactly to get the Fermat's quadruple. So 138D is a quadruple, then D has to be 120. And this, they had to use linear forms and logarithms to do this. This was a difficult theorem. Now the natural question is, can we find a Diophantine quintuple? Can we have a 5-element set which satisfies this property? It's a very basic question. And what do you think the answer would be? What would you guess? Do you think we can have a 5-element set of satisfying this property? You can conjecture. I mean, you will not be held accountable for making a wrong statement. No. All right. That's the right answer, and it has been resolved. But okay, we'll talk about that in just a minute. But one thing to note here is, okay, first question is, will these sets be? Can we have an infinite set which satisfies this property? That is rather easy to answer, and that comes from another Diophantine equation, which are called elliptic curves. Equations of this form: y square equals to some cubic in x. And it's a result of Siegel, who shows that there are only finitely many integer points on these type of curves. So clearly, whatever set you give me, it has to be a finite set. We cannot have infinite set. And then, okay, I am moving a little fast because I am sort of out of time. Then it was as late as 2019 that this problem has been successfully resolved. And we know that there are no Diophantine quintuples. But we still don't know whether, what happens for rational numbers. And there are many variations of this question that we still don't know the answer to. But in fact, there are no Diophantine quintuples. But we still don't know the answer to Baker-Davenport's earlier theorem that I posted. If you have a Diophantine triple, can it be uniquely extended to a Diophantine quadruple? That we don't know the answer to. Is it true for all Diophantine triples? That we do not know. Okay. And all right. So in this context, I will how okay is it if I take 1 or 2 more minutes? Okay, yeah, sure. All right. So then now we'll try to look at some generalized versions of Diophantus's problem. We will call them generalized Diophantine tuples. So we'll say Diophantine M tuples satisfying property Dn. If we with the exact same thing, except instead of taking aij plus 1, we take aij plus n. We can ask the same question for Diophantine tuples with property Dn. And it turns out that there are Diophantine quintuples here, so the first conjecture fails. And there are in fact Diophantines, like you can in fact also find 6 elements, but it is hard to find 7 elements or some sort of thing like that. But we can talk about how large can these sets be, and the best known bounds are something of this form. If you say that all the elements in the set are large enough, as compared to n, like I am looking at aij plus n being a perfect square. If I say that all the elements ai's are greater than, let's say, n cube, then there are only finitely many such. The size of this set is at most finite. This is what is known. This basically means that all my elements a1, a2, an, whatever I take, all these elements are greater than n cube. then aij plus n being a perfect square can only happen can only happen for at most a finite set of the size 24. But if I allow smaller elements, it's still possible that it is a large set, and the best known bound is something like the order of log n. Okay, and this is the precise bound. This is less than equals to some constant times log n. That's the best known bound. Of course, we should expect much better, but this is the bound that is known for sure. You can ask the same question instead of squares for kth powers, cubes, fourth powers, and so on. And in this context, we will call mkn as the size of the largest set, which satisfies the property that aij plus n is a perfect kth power. And mknl will be a size of the largest set, where each element in that set is at least n cube, or n to the power of l, something like that. So I just quickly want to go to the theorem. So these are the known things. If I take n is equals to 1, as in the case of Diophantine tuples, aij plus 1 is a kth power, then the answer is known to that, and we know the exact bounds. We expect it to be kind of like 3, at most 3 for large enough powers, if your kth power, which is 177th power or more. And unconditionally, the other results are pretty weak. They're like some polynomial in n. And recently, I just want to conclude with stating some of our theorems. Recently, we were able to show that this is the work with Soo-Young Kim and Ramamurthy. We were able to show that the largest size of this mk and l is actually bounded, just like we had 24 in the other case. This is bounded above as some kind of a function in k, and in general it is bounded above by some constant depending on k times log n. And over the summer, with some summer students, some BSc students just of your age, we proved the exact precise version of that. We proved that mk and l is actually bounded above by this particular constant depending on k. This is much better than what we had unconditionally before, which is like a polynomial in n. And then we also showed that if your n is much larger than k, we kind of get the size is less than this constant times log n. So where phi is your Euler function. Okay, I apologize for rushing through the last part. I really wanted to show some problem of Diophantus, because that was the theme, some problem which is still relevant. We are still working on it. I wanted to highlight that, and but I ran out of time, so I had to rush through the last part. But I'm very happy to take any questions. I think that's where I end. Thank you. Yeah, if you have any questions, now is the time.
You can ask questions from any part of the talk.
Yeah. Just feel free to ask any questions that you have, even if it is not related to the talk. Yes.
There you are given one example that Fermat forms that first equation.
Yeah.
That is 1, 3, 8 and 120.
Yes.
And Euler gave the general possible as A, B and A plus B plus 2R.
Yeah.
And the last one is 4 times of R plus A and R plus B, right?
Yeah.
But when you solve that, you will be getting the last number as 60 and not as 120.
Is it? Okay. Then, okay, if that is so, then there is some problem with the way I wrote it then. Okay, let's see. Let me just try to do it quickly here. So you have A is 1, B is 3, and R is 2, right? So you have 4 times 3 times 5. I see. Okay, then maybe I made a mistake somewhere. Maybe this is 8 or something. Yeah. Sorry about that. Yes, thank you. Yeah, thanks. That's a good catch. That means you're paying attention. Very good.
Any more questions? Okay.